Hello everyone. Today we're going to talk about thermodynamics. The reason I changed from mechanics to thermodynamics is because I think mechanics is too mathematically intensive. And I think I want to start with something less mathematically intensive, although if you're talking about true thermodynamics, it's pretty difficult. But I'm just going to cover the basics for thermodynamics. So yeah, basically what we're going to talk about today is temperature and heat, ideal gas, and the two laws of thermodynamics. We're not going to talk about the third law because there's not much application for the third law for problem solving. Although it's pretty important though, so don't get me wrong for that. For this video, we're just going to talk about temperature and heat and ideal gas, and the two laws of thermodynamics. We're probably going to leave it to the next video. The first thing I'm going to talk about is the concept for temperature. Temperature, when we're talking about temperature in real life, we're talking about how cold and hot a thing is. In physics, we're talking about the kinetic energy of the molecules in one material. So how does this relate to the thermodynamics topic that we're talking about? Temperature, in fact, relates to this concept called thermal equilibrium, which is described by the zeroth law of thermodynamics. Thermal equilibrium is essentially saying, let me just give an example. When you're using a thermometer to measure the temperature of a material, for example, if you're measuring how cold a lemon tea is, you have to put it inside the lemon tea, and then you have to wait for like 5 to 6 minutes for it to kind of settle down and have like a steady measurement of the steady level of the measurement of the temperature of the lemon tea. So this state, when it becomes steady, is called thermal equilibrium because the amount of heat in two materials, in this case the thermometer and the lemon tea, is exactly the same. So the zeroth law of thermodynamics kind of talks about if a system A is in equilibrium with system B, and if system A is also in equilibrium with system C, then system B and C are in thermal equilibrium with each other. So let me just draw a brief diagram for that. So if you have A, you have A, you have B, and you have C. So basically what happens is if you have these two are in equilibrium, and if these two are in equilibrium, then these two are also definitely in equilibrium. This is a very important concept in physics, and scientists actually didn't realize it until after they found or they formulated the three laws of thermodynamics. And they call it the zeroth law just because they don't want a fourth law, and it's not that important, but it's a very important fundamental concept, like a very important fundamental concept, but not important in terms of further scientific research. So that's why they call it the zeroth law. How do we actually measure temperature? So there are many ways we can measure temperature, and there are many scales that we use in the world, but mostly we use in daily life we use Celsius scale, and I believe in the United States they use Fahrenheit. However, in physics we don't use either of these. We actually use Kelvin, which is like pretty widely used. I believe it's also used in chemistry. And Kelvin is basically based on the concept that in the universe there's a thing called the absolute zero, which is like the lowest temperature possible for a material, and that temperature is negative 273 degrees Celsius, around something like that. And then in Kelvin it's just 0 Kelvin. So this is called the absolute zero, which means that there are no kinetic energies in the molecules in the material. So from here on, I'm always going to use the Kelvin scale when we're talking about temperature. So just a heads up for that. Next up, we're going to talk about heat and how heat constitutes expansion. So when we have a temperature change, there's either going to be an expansion or contraction in a material. So if you guys watch like, I forgot like what talk show it was. It was like James Corden or something. And then basically if you there's like I remember there's this one episode where I think you put like extremely hot water into a big pot, and then you put this big pot into ice water, and what happens is the pot actually breaks. So the reason for that is because of this concept of expansion and uh, contraction. When you put hot water into a pot, the material inside the pot expands. However, if you put it in ice water, like the outer surface contracts. So that's why I think it just explodes or something. I kind of forgot what happens. So yeah, when we're talking about expansion, we're talking about this concept of linear expansion and volume expansion. So linear expansion is one dimensional. So for example, if we have a metal rod and we put it in here or something, then the metal rod, we expect it to kind of grow longer. So if you see those like bridges, and if you see like the gaps between like the material on the bridge, the reason that they add the gap is because during summer, it becomes really hot, so the material kind of expands on the bridge. So what happens is, if you don't have that gap, there's no space for the material to kind of expand, which is why um, the road will become deformed. That's why they add a gap, so to kind of like expect this kind of expansion. Volume expansion is essentially the same thing. It's just like the total increase in volume. So of course there's a mathematical equation for this, and it's actually not really complicated. So when we're talking about temperature change, we expect the temperature change to be proportional to the change in length. So what we have is the change in length is equals to the coefficient of linear expansion, which is we denote it as alpha, times the initial length of the material times the change in temperature. So that's basically the formula that we have. For volume expansion, it's essentially the same thing. So we have the change of volume equals to the coefficient of volume expansion times the initial volume times the change in temperature. If you look down here, I have two tables that I took from a textbook. Basically, this is like the table for like really common materials, like the coefficient of linear expansion and the coefficient of volume expansion. If you notice, if you look at these materials, you'll see that the coefficient of volume expansion seems to be 3 times of the coefficient of linear expansion. The reason for this is, for example, if you have solid, then this part expands by this part expands by this, and this part also expands by this. And if you calculate the volume of a material, you always times it by 3 times. So that's why what we have here is 3 times of the coefficient of linear expansion. Obviously, this is like a very vague concept, but this is like basically how I try to get you to kind of understand why it's 3 times, although it's not exactly the reason when you're using like calculus to derive it, but I'm not going to show the derivation in this video. And keep in mind that don't assume this kind of 3 times relationship always exists. It only exists for solids. So if you look at the liquids, it doesn't. It's just completely unrelated. So next up, we're going to talk about heat measurement. So for heat measurement, there are we basically relate. How do I say this? We kind of calculate heat by denoting how much energy we need to change the temperature of a material with mass m. So basically, heat is a form of energy, and to rephrase, it's just basically how much energy is needed to change the temperature of a thing. However, there are many different kind of conditions, I would say, and there are mainly 2 conditions. I'll illustrate this by drawing a big diagram. Sorry for the wanky line. So for y-axis, we have the temperature. For the x-axis, we have the time. So basically, if we're heating up a material, we would expect the temperature to go up as it changes with time. So let's say we're talking about water, and this is 0 degrees Celsius, this is 100, which is the freezing point and burning point respectively. When we're increasing, when we're using the heat to, when we're heating up the water, we basically expect this. So this is the solid state. However, when it reaches the freezing point, it actually stays horizontal for a while, and then it goes up again. And at the boiling point, it stays horizontal again, and it goes up like indefinitely. So basically, this is the horizontal line is the heat change, the state change. And when we talk about state change, how do we measure the heat? We measure heat by using, since there are no temperature change, we cannot kind of relate heat with, temperature, the change in temperature. So we use what's called the latent heat. And this is these parts. So these parts where the temperature is increasing, we measure the heat by specific heat or molar heat. So molar heat is basically relating the change, the heat with number of moles, and specific heat is just the mass. So I'm just gonna write the equation down here really quick. So C denotes the specific heat capacity. And when we're talking about specific heat capacity, we usually did the formal definition is this. It's basically the change of heat. Let me rephrase it. The heat energy needed to change to increase the temperature by 1 Kelvin per unit mass. Basically, that's the definition of specific heat. It's the same for the molar heat, except it's in number of moles. So it's like per mole instead of per mass. And latent heat is a little bit different. It's just basically the heat is proportional to the mass, and this is the latent heat capacity. And we cannot use specific heat capacity for state changes because, as I said, the temperature doesn't change. So you have no way to kind of calculate the heat involved. So yeah. There are also 3 ways of how heat transfers. So the first way is conduction. So when we're talking about conduction, we're kind of talking about how the objects touches each other. So for example, if we're A and B, heat goes from A to B. Convection is basically the mass translation of current. So for example, if we have like boiling water, of course it's a really small amount. The heat current kind of circulates around like this. So that's how convection occurs. And in my videos and in this series, I'm not going to talk about convection a lot because there's not really a clear way of relating convection with heat using a mathematical equation. So I'm just it's basically the concept of current interchanging and therefore producing this kind of convection way of transferring heat. Radiation is very interesting. So radiation, let me think. Radiation is quite unconventional because when we talk about heat transfer, we imagine physical contact between 2 materials. However, if we think, let's think about this. If we have to have heat contact between 2 materials, then Earth today will be, why would it have heat from the sun, right? Because there's no contact between the sun and the Earth because there's vacuum in the space. So how do you actually transfer heat? Here comes the concept called radiation. So radiation is basically the heat transfer process using electromagnetic radiation. And the radiation heat, there's a concept called the radiation heat current, and it kind of relates to the surface area of a material. And we're gonna cover more in the electromagnetism unit. So I'm just gonna talk about like the mathematical models here. For conduction, the general formula is this. So we have the heat current. I kind of forgot about talking about what heat current exactly is. So heat current refers to um, the heat going through like a cross-sectional area per time. So basically that's the definition of heat current. And when we're talking about heat current, it's when I said it's the heat per time, we can also denote it as dq over dt. And this is usually the form. So K is the thermal conductivity of a material. It's different for every single material. A is this cross-sectional area. TH and TC is basically the hotter temperature of one side. So if you have like two materials, this is 35 degrees, 35 Kelvin. Actually, that's too low. Sorry. When we're talking about like, for example, 400 Kelvin and 300 Kelvin, then TH is 400 Kelvin and TC is 300 Kelvin. And D is basically the thickness. So the thickness. And K is A is just the cross-sectional area, as I said. For convection, there's not very clear mathematical formula. For radiation, it's very interesting. It's actually H times. So basically the constant, this is the surface area. This is the emissivity. So the emissivity is basically a number between 0 and 1. 0 is a black body, I believe. A black body is basically a black body. Sorry, it's not 0. I'm messing up. A black body is basically, it absorbs every single electromagnetic radiation. So a black body. So it doesn't deflect any any energy off. And 0 is basically like a black body is basically idealized radiation service, and 0 is basically the like it doesn't absorb any heat at all, so no heat at all. And the number between 0 and 1 is just ratio to the black body, like the idealized surface. Sigma is I believe it's the Stefan Boltzmann constant, and in fact, scientists discovered that the heat and the temperature is, heat is proportional to temperature to the power 4, and that's I believe that's how they found it. Like I think empirically, I'm not sure. So that's basically the ways of heat transfer. And this is the last concept for this video, ideal gas. So what exactly is an ideal gas? So there are many assumptions for ideal gas. The first assumption is basically the collisions between the molecules, I believe, is elastic, totally elastic, and their motion are like completely frictionless. So the molecules do not lose any kinetic energy. And I think the second wait, let me just recall for a moment. The second assumption is the total volume of the individual molecules is smaller than the volume the gas occupies. And the third assumption is like I think there's no intermolecular forces acting on the molecules. And I think that's the three assumptions for ideal gas. And if you guys think like I said something wrong, or if I missed something, please do share them in the comments. So yeah. So basically, an ideal gas, there's this. We often use moles to calculate stuff. The reason for that is because like it's kind of related to chemistry, but moles is easier to calculate, especially when we're talking about the ideal gas law. So how do we relate mass, moles, and molar mass? So basically, the mass of an object is basically the number of moles times the molar mass. So that's it. For ideal gas law, basically for ideal gas law, we have PV equals to nRT. And PV equals to nRT is it composes of many other laws that they found. For example, how P is inversely proportional to V, how P is proportional to T, and how V is proportional to T when P is constant, when V is constant, when T is constant. And I kind of forgot what those laws are called. So yeah. This is basically the law you see when we're talking about ideal gas, and it's commonly used in physics. I'm not sure if it's commonly used in chemistry, but definitely physics, like it's commonly used. This one is not really commonly used because like the model it's too complicated, and I kind of forgot what the equation is, so you guys can like easily search it up on Google or something. And we're also not gonna like talk about it in depth in this video. So yeah, that's basically like it for this video. And for next video, I'm gonna continue with ideal gas, and I'm gonna talk about the first law of thermodynamics. And the second law of thermodynamics, I might have to leave it for a bit. I'm not gonna talk about it like too much because it's quite complicated. So yeah, I hope you guys enjoy the video, and I'll see you soon in my next video. So bye.